Alright, so we're looking at a sample distribution for a proportion again. So we're going back to our applet, and I just want to go over some things. So in our situation here, we know that in this case 70% of our population has some attribute. Okay, so we're going to sample from that population. Okay, and our n size is 50. Okay, so I want my sampling distribution to come out so that I could use a normal model. So that means that NP and NQ should both be at least 10. So 70% of 50 is 35, and 30% of 50 is 15. So we should be fine. And I'm going to take 10,000 samples of 50. Okay. And if I do that, again, what this is right down here is this is the count, and this is the proportion. And if we look at this, our proportion right here is in our sample distribution is centered right around 0.7. Okay, which we know that our population distribution has a p-value of 0.7. So our p hat came out to be 0.7. And we also know that our standard deviation here is 0.0652, right? So how do we get that? Well, we would do the square root of p, which is 0.7 times 0.3. Okay, over n, and our n size here is 50. So the square root of pq over n. And what does that equal? Well, that equals the standard deviation, not the standard error, standard deviation of our sample distribution, which is going to be p hat. Okay, that's going to be the standard deviation of our sample distribution. Okay, so what we're going to be looking at in our in this chapter right now is we're going to be looking at hypothesis testing. And when we do a hypothesis testing, we're going to be hypothesizing what p is. So we then can now find the standard deviation, because if we hypothesize what p is, then we can hypothesize what q is, and we now can use the standard deviation. And we know that our standard deviation, this standard deviation will work for every single sample distribution for proportions that has a p-value of 0.7 with a sample size of 50. Okay, and this is what our sample distribution would look like, and it passes our success-failure condition, so we're good to go. We have a sample distribution that's normally distributed, so we're now able to apply all these good things that we know about normal models in order to do our hypothesis testing, because our conditions are now met. Alright, so I want to start the chapter by going over our blueprint for inference. Okay, and we talked about we're going to use this basically whenever we have an inferential situation. Okay, now just a quick review. What's an inferential situation? An inferential situation is we have some population, and in our population we have parameters. So in our if we're dealing with proportions, then those parameters are p and q. Okay, if those are means, then those parameters are mu and sigma. Okay, and we take some sample from that population, and that sample has to be random or representative of the population. And in our sample we get statistics. Stats. So our stats, if we're dealing with proportions, we're dealing with p hat and q hat. And if we're dealing with means, we're dealing with x bar and the standard deviation of the sample, S of x. What else we get when we sample, okay, is we get variation from sample to sample. So we wind up with a sample distribution, and we know that p hat's going to be a pretty good approximation of p, but chances are it's going to be a little off. And the same thing with x bar with mu, okay, and s with sigma. Okay, so we got to account for that variation. Okay, and then we do our inference test. So we do our inference test. So last chapter we did a confidence interval, and then from that we then infer something back about the population. Okay. So that's our whole concept of inference. Okay. So we have our blueprint. So the first thing is we're going to do our parameter, and right now we're going to have p, which is the proportion of something, or we're going to have mu, the mean number of something. Well, in this chapter we're looking at proportions, so we're not going to go to mu yet. Okay. Alright, now H is a hypothesis, and we're going to formulate a hypothesis. So our null hypothesis is always going to be that P equals something. Okay, so where does this hypothesis get generated from? Well, a claim is made. Okay, so you get a bag of M&Ms, and the M&M company claims that 15% of all M&Ms are yellow. So you start eating M&Ms and you say, I don't think that's right. I think they're lower. Okay. And you then go and you test it. Okay. Now this is called the null hypothesis. And you then do whatever test you're doing. So in this case, your alternative hypothesis is always one of three things. P is less than something, P is greater than something, or P does not equal something. And this is called the alternative hypothesis. Okay. So in this case you would say, okay, my null hypothesis is P equals 0.15 and my alternative is P is less than 0.15. I'm trying to prove that M&M's is wrong. The M&M company is wrong. Okay. Let's say that we find that exercise helps cure heart disease. Okay, so we find people who have heart disease, and we find the proportion of them that exercise is like 33%. And then we go and we bring them in and we show them how to exercise. okay, and the types of exercise they should be doing and how long they should be doing it, and we give them a program, and then we follow up on it, and we sample people who have heart disease, and we see how many of them are exercising. Okay, well then we would want to see that P is greater than 33%. We'd want to see that our program worked. Okay, we'd want to see evidence that our program worked. Okay, so the null usually comes from a claim, and the alternative is you're trying to prove the claim wrong. That's basically what it comes down to. This hypothesis is always formed before the data is collected. You don't collect the data and then say, okay, I'll form my alternative hypothesis. No. Okay. The next thing is assumptions and conditions. So again, there's three that apply to your sample: random or representative, less than 10% if you're sampling without replacement, and some kind of independence condition. And then the fourth condition is a condition that allows you to use a normal model. Okay. So since we're dealing with proportions, it's going to be NP is at least 10 and NQ is at least 10. Now we got to name the test. So last chapter we had a one proportion confidence interval. This one's a one proportion hypothesis test. T, you remember, is test parameters and statistics. Now, where do your parameters come from? All right, because remember, most of the time your parameter is not known, but in this case your parameter is claimed. You know, somebody makes some claim. Okay, so M&M's is making a claim that 15% of their M&M's are yellow. So that's where our parameter comes from. That's their claim. We're trying to disprove it. Okay. Now O is obtain big P. Now in order to obtain big P, here's what you got to remember. Back in chapter 6, when we use normal models, we'll learn how to do something called a z-score. And z equals some number minus the mean over the standard deviation. Okay. So in this case, if I'm dealing with a sample distribution for proportions and I'm looking at the population distribution, what am I trying to what is my p hat trying to approximate? Well, it's trying to approximate p. So if p hat is the mean of my sample distribution, what must be the mean of my population distribution? Well, it must be p. So then my mu for my population distribution must be p, the proportion that actually exists. The standard deviation we talked about in the video is the square root of pq over n. As long as we have p and q, we can do standard deviation. Well, where does p and q come from? Well, it's hypothesized. Okay. And then x is going to be how far from the mean my data shows my proportion to be. Well, what's that going to be? That's going to be p hat. So here's what we're going to wind up with. We're going to wind up with p hat minus p over the square root of pq over n. And that's going to allow us to use a normal model as long as we meet our success failure condition. All we've done is we've just taken this and applied it to proportions. Okay? And from that, we're going to calculate this value called big P. Okay, and I'll get into that in a minute. Okay. Now, M, we got to make a decision. When you do a hypothesis test, you got to make a decision. Did you prove this wrong? Yes or no? That's basically what it comes down to. There's the null hypothesis. Were you able to disprove it? Yes or no? Okay. Now, when we reject the null, we accept the alternative. Now we have a threshold of which we reject that, and I'll explain this in a minute, but we generally reject at the 0.05 level. What's 0.05 represent? It represents 1 in 20. So if there's less than a 1 in 20 probability of getting what we had, then it's pretty much unlikely that that's merely by chance or variation. There's probably a significant difference from what we thought or what we hypothesized P to be. Okay. Now, when we make a decision, basically what we're doing is we're putting P on trial. Now, if you know anything about a court of law, there's only two verdicts that can come back in a court of law. Right? One is you can find a defendant guilty, or you can find a defendant not guilty. What you cannot do is find a defendant innocent. All you could say is the defendant's not guilty. Well, what does that mean, that they're innocent? No, it doesn't. Okay, we could find somebody not guilty because we didn't have enough evidence to convict them, but they are guilty. So we can't say that they're innocent. We can't ever say someone's innocent. All we could say is we didn't have enough evidence to come into the courtroom and convict. So here's what we could do. We could fail to reject the null. Okay. But we can't accept the null. Can't say, oh, the null is true. All we could say is we don't have enough evidence to disprove it. Because the null may not be true, but because of sampling variation, you may not have enough evidence to reject it. And our second alternative is we can reject the null and accept the alternative H of A. That we're allowed to do. We can say, okay, we have enough evidence to say that the null is false and the alternative is true. Okay. And lastly, state our conclusion in context. Always in context of the problem. Alright, so there's our blueprint, and that's how we're going to proceed as we go into this chapter and we start looking at hypothesis testing. Alright, so in example 1 here, a 1996 report from the U.S. Consumer Products claims that at least 90% of all American homes have at least one smoke detector. The city's fire department has been running a public safety campaign about smoke detectors consisting of posters, billboards, and ads. Okay, so the city wonders if this concerted effort has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes and find 376 of them have smoke detectors. It's a strong evidence that the local rate is higher than the national rate. Okay. So our parameter here we're going to have is P equals the proportion of homes in this town that have at least one smoke detector. The null hypothesis is that P is 0.9. So the town's proportion of houses that have smoke detectors is the same as the national average. Now, what are we trying to prove? Well, we're trying to prove what this last sentence says. Is this strong evidence that the local rate is higher than the national rate? So the alternative is that P is greater than 0.9. So what this means is we only care if it's greater than, we don't care if it's less than. So this is called a one-tailed test. Because we only want values that are greater than 90%. Okay, we don't care if it's less than. If it's less than, then it doesn't prove what we want it to prove, and we would fail to reject the null. So that doesn't help us. We only want evidence if the program worked. So our assumptions and conditions. Well, they told us here we had this sample homes were randomly selected. Actually, we're going to put down 400 homes were randomly selected. Each home is independent in its smoke detector usage. Okay, so one home does not affect another. 400 homes is less than 10% of all homes in this town. In our area, that would certainly be true. If this was in a rural Montana or something like that, that may not be true, but we'll assume it's in a town like the one that we're in, and we'll be fine. Okay. And now we got to do success failure. Okay, well, do we know what P is? Yeah, we hypothesize what it is. So we're going to use P. Now you could use P hat. You already know what NP hat is. You know it's 376. Okay, so then NQ hat would be 24. Okay, you can use that. That's fine. Either one is acceptable. Okay, but when you have P, it's better to use P. So I'm going to do 400 times 0.9 is at least 10, and 400 times 0.1 is at least 10. So a normal model is appropriate. Name our test. This is a one proportion hypothesis test. By the way, your calculator will call this a z-test. Remember, you did a one proportion z interval. This is called a one proportion z-test on your calculator. Okay, the player's in the game now. So now we got P, Q, N, P hat. P hat is 376 over 400. Okay. So that's our sample proportion. And then Q hat would be our sample failures. Okay, so to obtain our p-value, we have to find a z-score for this. Okay. So our z-score is basically how many standard deviations from the mean is this 0.94. Okay. So what we observed was 0.94. Our mean we expected was 0.9, and then we did the square root of P, Q over N. Okay. So that must mean that this is 0.04 on top. And then we got to do square root, and 0.9 times 0.1 divided by 400, close parentheses, and that's 0.015. And 0.04 divided by 0.015 is 2.667. So So this is 2.667, which is almost 3 standard deviations from the mean. And remember, we talked about things that are generally greater than 2 standard deviations from the mean are generally our threshold to say that that's pretty unlikely to happen. All right, so let's go to our calculator now, and let's just have it knock that out for us. First, I'm going to just show you how to go to second distribution and go to norm CDF. And our lower bound, basically the proportion of houses that we have in our town starts at 0.94, and it goes up to 100%. And our mean is 0.9. And our standard deviation for this sampling distribution would be 0.015, which is the square root of PQ over N. And that comes out to be 0.004. Okay, so here's what this looks like. So remember, whenever we do a normal model, we draw a picture. So we have a sampling distribution where we think the mean mu sub p is 0.9. It's not a negative, it's 0.9. But we got a p hat of 0.94 or higher. Okay, because why higher? Because we want to see that it's greater than. We want to see only if it's greater than. Okay. And this shaded region is 0.004. That is your big P. We call that p-value. Now I compare that to 0.05. And 0.004 is much less than 0.05. 0.05 is 5%, 0.004 is 0.4%. So 0.004 is less than 0.05. So what I'm saying is, if this is true, then this shaded region is highly unlikely, because there's only a 4%, there's only a 0.004 chance that we would have gotten this shaded region with this sample if this null hypothesis was true. So it's not likely we would have gotten that sample. So what does that mean? Well, that must mean that the null hypothesis must not be true. Okay. So let me show you how to do this now. When you do this on your paper, this has to go on your paper, and then you go to stat tests and one prop z test, and p sub 0 is your null hypothesis, and that's 0.9. X is the number of successes, that was 376. N is 400, that's your sample size. We're doing a one sample t-test, so we want to see if it's greater than, so that's how we did that. And then we'll draw it. Okay, so my guess is, yeah. If you have anything on your residual plot is on, then that messes this up for whatever reason, so just turn it off. So go back to stat test, one prop z test, and we'll draw that. So look what comes up. It doesn't even show that it's shaded over here because it's such a small region, but there's our z-score, 2.667, and there's our big p-value, 0.0038. And that gets drawn on your paper. So basically you can go from this step right here to this step over here. You don't have to do all this. You don't have to do the calculation. You just got to show the work, and then you can have the calculator do the calculation. So what we're going to do here is we're going to reject H sub O at the 0.05 level. Now this level can change. I could make it the 0.1 level. Well, if it was the 0.1 level, I'd still reject it because this is below 0.1. I can make it the 0.01 level. I'd still reject it at the 0.01 level. Okay? But they didn't tell us, so we're going to do it at the 0.05 level. Now, what's our conclusion? Now, I compare this big p-value to my 0.05, and it's much lower. So I'm going to say there is strong evidence that the proportion of homes in this town that have a smoke detector is greater than 10%. 90%, I'm sorry, 90%, because that was our hypothesis. So what we're saying is there's evidence that it's greater than 90%. I would also note it appears that the program was successful in increasing smoke detector usage. Again, why wasn't I dogmatic with that? Well, I said it appears. I didn't say the program was successful. Well, maybe in this town people used a lot of smoke detectors before they did the program. So maybe the program really didn't have an impact. Maybe people were already aware of this type of situation and already were using smoke detectors. So I'm just going to put down it appears. So I kind of give it a soft answer, not a hard dogmatic response. Okay, so interpret, what does this p-value mean? Okay, what does the p-value mean? So here's what we got. We think the mean is there. We got a p-hat of 0.94. We shaded to the right. This came out to be 0.004. So what is this graph telling us? Well, it's telling us that there's a 0.004 chance of getting this region right here if this is true. Well, what is this region? Well, this region represents a p-hat of 0.94 or higher. Okay? So in context, okay, there is a 0.004 chance, or 0.4% if you want to put it, of getting a p-hat of 0.94 or higher, because we shaded to the right, if you could put mu sub p or p equals 0.9. So if that's true, that's the probability we would get that region. That's what the big P value means. That's what this big P means. Now we do a 90% confidence interval, and once we do all of our conditions and everything, we don't have to go and do phantoms all over again. We just go and we just write the formula and then interpret it and calculate it and interpret it. So remember, confidence interval statistic, which is p hat plus or minus z times the square root of p hat q hat over n. So in this case, we would do 0.94 plus or minus 90% confidence interval. Remember what z was? It was 1.645. If it was a 95%, that would be 1.96. Now, in a confidence interval, I proceed as if I don't know what p is. So I'm using p hat and q hat because I'm trying to trying to estimate what P is based on the statistics that we got. So we're going to go to stat tests, 1 prop z int. That's 2 prop z int. Let's try 1 prop z int. There it is. Okay, so x is the number of successes, 376. N is our sample size, 400. We got a confidence level of 0.9. So it's 0.92 to 0.96. Now notice that that comes to that if we were to use the confidence interval to test our hypothesis, here's our hypothesis, right? There's the confidence interval we got. Notice we would come to the same conclusion. Why? Because 0.9 is not in the interval. Our entire interval is above 0.9. So our evidence is that P is above 0.9. Okay, so we are 90% confident that the proportion of all houses in this town that have at least one smoke detector is between 0.92 and 0.96. So we're trying to figure out here what's the proportion of all houses in the town based upon our sample. Okay. So 90% confidence interval corresponds to a one-tail test rejected at the 0.05 level. Why is that? Because if you look at a normal model and you were to do a 90% confidence interval, which means we do the middle 90%, we're only looking at one tail. So if we do a 90% confidence interval, we're either looking at this tail, well, there would be 5% in that tail, or we're looking at this tail. This over here represents an alternative hypothesis of P is less than. This over here represents an alternative hypothesis of P is greater than. If I'm looking at P is greater than, then I'm only looking at this region here. I will only reject if I get a sample that's in that region. And the same thing if I'm doing an alternative hypothesis of P is less than. I would only reject if it came over here in this region. So that's basically why it's a one-tail test. Okay, because you're only looking at one of those tails at the 5% level. You don't use the other tail. The other tail is irrelevant to your test when you do a one-tail test.